at the moment, what we have is the possible locations of an electron in the Bohr orbits, and the whole time I've been telling you that that's not really how things work. So honestly, this is all like completely useless at the moment. So what we want to do is maybe ask something that isn't useless. What about the energies? So we could ask the energies of Bohr orbits. And the first question is, what is the energy of a thing in such an orbit? Well, I don't see any friction. So it's going to have mechanical energy only. So it's going to have kinetic energy, and it's going to have potential. So the total energy is going to be the kinetic energy, the motion of the electron in the orbital, which, this is kind of a semi-classical treatment. This is not true quantum mechanics. This is the Bohr model. And it's going to have potential energy, specifically the potential energy associated with the Coulomb force. Okay. So the total energy would be 1/2 mv squared. And we know that we can express that with momentum, right? We can pull that trick again. And the Coulomb potential, which is, we'll call it K e squared over R. And we now know that this could be Rn. So that's the electrostatic potential. And that K is the 1 over 4 pi epsilon naught. Okay, so we'll do the same sort of tricks. I'll leave the details of the derivation out. But you could totally do the same thing. So you could say that P equals mv, and P is also equal to h over lambda. And furthermore, lambda is equal to 2 pi Rn. So we've got P squared downstairs, and we've got P there too. So we also know that, Rn. And then we have some math that can happen. And I'll just like ... and get En. I will write the full thing, and you'll realize why I ... dotted. This is literally, even after teaching a whole bunch of intro physics, like I can't remember this to save my life. And also it's the Bohr model, so it's really, there's no point in remembering it. Okay. So ... energy depends on n, which one of these orbitals you're in. This is the n equals 1 orbital, 2 orbital, 3 orbital, goes out to infinity. The important thing, sorry, this is negative because it's in a gravity well. So the important thing about this is literally everything in here is a constant. Planck's constant, mass of the electron, this electromagnetic constant K, fundamental charge pi. And this is an integer. So let's just evaluate this once. And this is this is unitless. This actually is an energy. So there's a thing called the electron volt. And the electron volt is the energy that an electron picks up when it goes through 1 volt. Yeah, sort of wonderful number. I'll give you the joule equivalent in a second for 1 eV. But I just want to admire like the clean form of this and what this actually tells you. So what this tells you is everything that you need to know about the spectrum. So we did this in this kind of like backhanded way. So let's say that I go from one energy level to a different energy level. So let me leave that here. So again, we're glossing over a lot of the mysteries of quantum mechanics, but let's just say that a quantum jump occurs and we go from n equals 2 to n equals 1. Okay? We're going to conserve energy so that energy leaves in the form of light, aka a photon, and this photon has some energy. that photon has the exact same energy that I dropped when I went from n equals 2 to 1. And I can figure that out. So my delta E would be minus 13.6 electron volts. And then we started at 2 and we ended at 1. Because we got the squared in the bottom. Does this formula look familiar? Let's say that we went from n equals 3 to n equals 2. In that case, delta E 32 would be minus 13.6 electron volts, 1 over 3 squared minus 1 over 2 squared. This looks a lot like the calculation we did with the Rydberg spectrum. So the Bohr orbits actually do get you Rydberg's formula, because this 1 over n squared shows up. And really, that is what n is. It tells you which orbital you went from, straight up in the Rydberg formula. So that's the orbital that you start at is the bigger number. The orbital you end at is the smaller number, if you're thinking about emitting light. OK. So let me just put in 2 notes. One is what the electron volt is, and the other one is hydrogen-like systems. Feel free to redo the derivation of all of this yourself and get what, get the number that should go in. But literally, 1 electron volt is the energy required to move 1 fundamental charge. It doesn't necessarily have to be an electron. Through 1 volt. And volts are SI units, so that's OK. So what this ends up being in energy, so 1 eV, the fundamental charge is 1 point times 10 to the minus. Sorry, something was beeping. Where was I? Yeah, 1 electron volt is the fundamental charge times 1 volt. So fundamental charge is 1.602 times 10 to the minus 19th coulombs times 1 volt. And somewhat magically, this turns the units. Number is easy to do. 1.602 times 10 to the minus 19th joules. Which is why 13.6 is nicer. So small amount of energy. OK, so that's note number 1, just the units on these. The note number 2, this is just really because it's in physics textbooks. And I guess if there's any reason for it to be in physics textbooks, hydrogen-like systems, it's really is a warning to not use the Bohr model for anything else. A hydrogen-like system is any number of protons. So there are Z protons, so the charge of the nucleus would be Ze. And that is positive. And there is 1 and only 1 electron. So the second you have even 2 electrons, like in a full helium, non-ionized helium atom, the electrons interact and just like the Bohr model completely falls apart. So people, the smartest people around working on this stuff worked on trying to extend the Bohr model to helium and lithium, and just, the whole thing blew up in their face. So hydrogen-like systems is basically you rip all of the electrons off but 1, and this still works. And there are 2 formulas that you could write down for hydrogen-like systems. So this would be, Z protons, 1 electron. And the relevant formulas would really just be a Z shows up. So the hydrogen-like system Bohr radii would be 5.29 times 10 to the minus 11. Let's do this instead. Let's do angstroms. 0.529, do that. N squared over z. Unitless, that's got to be a unit of distance. Just writing it this way because you might see this. 1 angstrom is 1 times 10 to the minus 10th meters. And then the energy would be minus 13.6 electron volts. And then the z shows up upstairs, squared. Okay, so the more protons pulling, the bigger the energy it takes to rip this thing off and ionize it. So the other meaning of the 13.6 electron volts is that that's the energy to ionize the hydrogen-like system in this case, or hydrogen without the z. So take the electron and completely rip it off. Okay? So let's do one last problem that puts everything kind of together with this whole thing. Let's just, with numbers, do the 3 to 2 transition. Okay. Ugh. What is the wavelength of light from the 3 to 2 transition? Well, the first thing I'm going to do is figure out the energy as I go from 3 to 2. The energy from 3 to 2 would be 13.6 electron volts, 1 over 2 squared minus 1 over 3 squared. Oops. Yeah, sure. We'll leave it negative. So that's negative 1.89 electron volts. So this is the amount of energy that the electron loses, the way it's stated now. That would be the amount of energy that the photon gains. So we have a 1.89 electron volt packet of light. That 1.89 electron volt packet of light would turn into something with a particular frequency. So this is the other half of the quantization hypothesis. So this is the Planck part, that this is all we'll, part of the reason to do this problem is just so you have some familiarity with this. So the energy of a packet of light, otherwise known as a photon, is Planck's constant times its frequency. This is for light only, right? So don't do this with an electron. Don't take the frequency of the electron and multiply it by Planck's constant. So this is 6.626 times 10 to the minus 34th joule seconds. And that frequency is, we'll just figure that out. We got to convert this to joules, and there is 1.602 times 10 to the minus 19th joules in an electron volt. And then we got to divide that by h. And that gives us a frequency. And I'll write the frequency because it's kind of interesting. And then we're back to normal sanity, no quantum world stuff, is that V equals F lambda, like normal wave stuff. So this would be, frequency would be c times the speed of light, or the frequency would be the speed of light divided by the wavelength. So the wavelength would be c, speed of light, 3.00 times 10 to the 8th meters per second divided by f. And we would get 650, should be 656, I rounded a bit, 656 nanometers. Okay. That was a lot. That was kind of fast. Basically, for the remaining 2 lecture days, we'll just do practice problems with this stuff.